Hey buddy, this is PSS. In order to facilitate the explanation later, you may wish to look at the common superconductor experiments. It can be seen that within a certain distance, no matter how you change the spatial position of the superconductor, it can be stably maintained, as if it is locked and magnetized. The phenomenon of flux pinning occurs. This is the characteristic exhibited by type II superconductors. There is no essential difference between type I and type II superconductors. It is mentioned in the description about the type II superconductor that a part of the type II superconductor can be passed through by the magnetic field. Is this really true? Is type II superconductor the result of type I customized modification? Or is a type I superconductor the real superconductor? Type II is just type I superconductor in non-ideal environment. In order to verify this series of assumptions, I propose the following hypotheses. 1. The process of making type II superconductor materials does not have the ability to completely remove impurities, resulting in a part of the material that is not diamagnetic. 2. After the type II superconductor is completely cooled by liquid nitrogen, the temperature of the superconductor will be rapidly increased by room temperature, causing the superconductor to locally transform into a conductor. 3. Type II superconductors have never been superconductors, and the previously described superconducting phenomena, such as the Meissner effect, have not been strictly verified. Shows only partial antimagnetic, not completely antimagnetic. Compared with pyrolytic graphite or water, it only improves the sensitivity of diamagnetism. For example, in the previous experiment where a frog was suspended in an energized solenoid, the magnetic field strength reached an astonishing 16 Tesla, thus deriving out, can zero resistance and almost complete diamagnetism exist at the same time? There is also a very strange phenomenon that you can hardly find any videos of measuring the resistance of superconductors on the internet. All of them show you the so-called magnetic levitation. Zero resistance and complete diamagnetism. As long as one of them is realized, it is a superconductor. Obviously, based on the diamagnetic experiments of superconductors observed so far, the entertainment nature is too strong. You can try to maintain the low-temperature environment while fixing the shooting position of the camera. Record for a long time whether the superconductor will have a slow falling trend. If there is a falling, what is the numerical change of the falling rate? Let me analyze it from my personal perspective. You can completely treat it as nonsense. I am more inclined to think that all current superconductivity is not rigorous. In other words, the superconductor you see now is a superconductor within the allowable range of error. According to the fact that the force on the superconductor in all directions of the magnetic field is balanced, it can be known that the superconductor has isotropic characteristics. As the superconductor gets closer to the magnetic field, both the repulsive and attractive forces become stronger. Then what factors affect the maximum value of the repulsive force and the attractive force? According to the observed phenomenon, it can be speculated that the upper limit of the repulsive force depends on the reaction force generated by the increase of the magnetic field strength, and the upper limit of the attractive force depends on the induction produced by the superconductor. The upper limit of the eddy current, that is, the upper limit of the magnetic field intensity induced by the superconductor,